Our last day of notes on electrons is probably going to be our easiest day of notes on electrons because we're going to eliminate a lot of the stuff we talked about earlier. The electrons that are most significant in chemistry are the outermost electrons because they're typically the ones that are involved in the chemical reactions and bonding that we're going to be learning about throughout the year. Those outermost electrons we call the valence electrons. So let's go ahead and define those. These are the outermost electrons. These are the electrons that are then furthest from the nucleus. When we're looking at the electron configuration, let's say we're looking at a configuration that is 282, that would be magnesium, the valence electrons would be this very last number, the electrons that are in the outermost principal energy level. So this would be the last, number in the electron configuration. That last number, you will notice as you look through the electron configurations in the periodic table, is never higher than 8 because that number only includes the electrons in the S and P sublevels. So it would include the 2 electrons from the S and at most the 6 electrons in P for a total of 8 electrons at most. So it's kind of nice to look at those electrons in a different way instead of having to write out an entire orbital notation. So we're going to use something called an electron dot diagram, or sometimes called a Lewis dot diagram, or a Lewis dot structure. And what this does is it actually shows where the valence electrons are found. It'll show us where the S and P electrons are, because what's most significant in bonding and reactions is the unpaired electrons, the ones that are sitting alone still on the bus. So this shows where the valence electrons are found. All right, so let me show you how this works. Let's say that I had something where the valence number was 8. So how we fill these in is important. Now, what isn't important is where we start filling in these electrons. The electrons are going to be represented by dots. Some people start on the left of the X over here, filling in the dots. I start on the top. That's what all my professors did, and pretty much is the standard in the SUNY system. Sometimes on the exam you'll see that they start on the left, which is kind of odd since I'm talking about a state university school, but that's for another day. So I'm going to start on the top, and if I have 8 valence electrons, I'm going to end up filling in 8 electrons around this X. X means some element X. X is often used as a generic element, like it is used in math as a generic number. We also sometimes use M because there is no element X and there is no element M. And M is often used when it's a metal, and X can be anything. So I'm going to start on the top, filling in my electrons. My first 2 electrons are going to be the 2 electrons that we would find in the P, or I'm sorry, in the S. In the P, if you recall, it has 3 orbitals. They're going to be here, here, and here. So what we just labeled, this is our S. And then the ones on each side, you wouldn't be drawing in this red part at all, would be our P's. This would be the P in the X plane. This would be the P in the Y. This would be the P in the Z. So when I go to fill these in, I'm still going to follow my bus seat rule. One goes here, one goes here, one goes here, before I go back and fill in the rest, like so. All right, so the order we filled these were 1, 2, 3, 4, 5, 6, 7, 8, like so. All right, so keep in mind that you can only have 8 electrons max. But then there can only be 8 electrons maximum. All right, let's try some additional examples. For these ones, we're going to need to use our periodic table to find the electron configuration. So I'm going to pull that in. And we're going to look at the last number in the electron configuration to figure out how many electrons we're going to be placing. For helium, we look down here, and the electron configuration is just 2. So we're going to be placing 2 electrons, keeping in mind those are both going to be in the S sublevel, and they'll both be on top. And like I said, you may actually see them on the left. That looks weird to me, so I don't do that. Now let's find arsenic. Here's arsenic, and its electron configuration ends in a 5. That's the valence number, and that's what we're using today. So we're going to place 5 electrons. 1, 2, 3, 4, 5. So it actually has 1, 2, 3 unpaired electrons. Those unpaired electrons are often used in making bonds. All right, next we're going to do cesium. I'll move this up a little. Cesium is in group 1 down here. It's one of our big ones, and its last number in the electron configuration, or the valence number, is 1. So it gets just 1. And the last one we're going to do right now is xenon, and xenon is actually a noble gas right here, and its last number is 8. So we're going to fill in 8. 1, 2, 3, 4, 5, 6, 7, 8. Will I know if you filled them in that order? No, I won't know at all, but it's best if you get in that habit so that you don't accidentally, like in this case up here, pair 2 up and then only have 1 unpaired electron. That's going to mess you up when we get to bonding. All right, next we're going to do a dot diagram for an ion. Ions have either gained or lost electrons. Since electrons are negative, when you have a negative charge, that means it's gained electrons. So sulfur typically has 6 as its valence number, but we've gained 2 electrons and it has 8. So we're going to fill those in. 2, 3, 4, 5, 6, 7, 8. But we want to make sure nobody thinks we made a mistake in filling those in, and that we did intentionally mean that it had those extra 2. So we're going to put our charge outside of some brackets. So whenever you have an ion, you're going to have some brackets, and you're going to have a charge on the outside. So that's what happens with a negative ion. When you have a positive ion, it must have lost electrons. In this case, it lost 2. So calcium, if you look at its electron configuration, the valence number is 2. So if it lost 2, it now has no valence electrons. So it has no dots on it and a +2 charge. The last thing we want to do on the front here is actually define the kernel. We've been using the kernel, and you don't even know what that is yet. The kernel is the symbol in the middle. And that symbol, since this whole thing needs to represent the whole atom, this symbol is representing the nucleus, so the protons and neutrons, and all of the non-valence electrons. So for xenon, it's representing the 54 protons, and depending on the particular ion we have, or isotope we have, it may have, 80 plus neutrons in there. And also it's representing the 2, the 8, the 18, and the other 18 non-valence electrons. So the kernel actually represents the nucleus and non-valence electrons. All right, so now we're going to try some dot diagrams here. We're going to need our reference table again, our periodic table. So I've pulled that in, and we're going to draw the dot diagram for neon this time. Here's neon, and neon's valence number, in case you can't see it, is 8. So we're going to do that. We put its symbol in the middle, and we're going to put 1, 2, 3, 4, 5, 6, 7, 8 valence electrons on it. Next, we're going to do it for phosphorus. Here's phosphorus here. I can barely read it. It's 5, has 5 valence electrons, so we put P in the middle. 1, 2, 3, 4, 5. Next, we're going to draw the dot diagram for calcium, and it has a valence number of 2. So we have Ca is the symbol, 2 electrons. Now we have some ions. We have F with a 1 minus. Since it's negative, it must have gained negative charges or electrons. Normally, fluorine has 7 valence electrons. Now it's going to have 8. So we have our fluorine, 1, 2, 3, 4, 5, 6, 7, 8. And it actually is going to need brackets with the charge. And you could do 1 minus like it is over here, or minus 1. It's interchangeable. Next we have magnesium. Magnesium, element 12 here, has a valence number of 2 typically, but in our example it's an ion is plus 2. So it must have lost its 2 valence electrons, so it gets no dots. But it does need the brackets and the charge, so nobody thinks we just forgot. Now iodine. Iodine is element 53, and it has a valence number of 7 typically. But for this one, we have a negative 1 charge, so it must have gained one of those negative charges or electrons. So we add in an extra, and then don't forget our brackets and our charge. And then the last one, they're just looking for a dot diagram of carbon. Here's carbon. Carbon has 4 valence electrons. What carbon does though, carbon's kind of naughty. It'll do whatever it needs to do. Carbon should look like this when we draw a dot diagram. But as you learn more about bonding, you'll find out that when elements bond with other elements, the goal is to end up with 8 electrons, whether they're stolen, which is happening here, or given up, which is happening here, or by sharing. And carbon typically shares. So what's happening with carbon is that if it were to share, it shares with these unpaired electrons. If it can only share 2 pair, it can only end up with 6 valence electrons. And the goal is to get 8. So carbon will actually move its electrons around, and silicon just below it in the periodic table will do the same thing and make it so that it can make 4 bonds. Now when it shares a pair with another atom, it can end up with 2, 4, 6, 8 electrons. We'll get more into bonding later on. This is the basis. These dot diagrams are what we use to show what happens during bonding, so it's really important that you understand this.